this is one small glitch. It will not move smoothly from slide to slide, but I'll have to make some adjustments now and then, but I hope you see everything well. If there is a problem, let me know. So look, so this is the outline. The talk is in three parts. The early development, it's a relatively young subject. It's 75 years old because model theory itself is a relatively young subject. It's unlike set theory or computability or even proof theory. It's younger, and its foundations and standards and canons were solidified only in 1950s because of the work in essentially two centers, in Berkeley on the west coast of the USA with Alfred Tarski, and on the east coast with Abraham Robinson. But of course, much was happening elsewhere, including Poland, where I'm from, and the school that was led by Professor Mostowski, who had many gifted and talented disciples. So model theory, and in particular model theory of arithmetic, as you will see, was very much a subject of interest, and many interesting developments come from Warsaw, where I was a student in 1970s. So the talk is in three parts. So first, there will be what I call early developments, and the choice of dates is very arbitrary, but you will see the difference between what was happening from 1950s, the first 25 years, and then what happened after that, and what's happening recently. And I have to be selective. So the second part will be just about isomorphism invariants for non-standard models of arithmetic, and I will explain what they are, and I will quote results about them. And then this is something that's close to my heart, something that I did most research on, is recursively saturated models and resplendent models of Peano arithmetic. And Frederick Engström, who's here, and I'm happy to see him, also devoted his life or his early life to this subject and had interesting contributions. So I will explain why we're interested in those models and what's interesting about them. I will sort of much of the material you can check later. I will give references later. There are two standard texts, so my immodest statement. Now, the first is Models of Peano Arithmetic by Richard Kay, that was published in 1991. It was a tremendous contribution to the community. It was the first textbook that brought together all the material that's necessary for the development of the subject in a kind of very, very thorough and extremely helpful way. So I will quote results from that are explained in the book, and so the book is really a standard, something one has to start with studying models of Peano arithmetic, but it covers a lot, but not everything. And so that's why later, it looks like 15 years later, Jim Schmel and I, we decided to write another book on a similar, now it's titled "On the Structure of Models of Peano Arithmetic," that covers all those areas that Kay's book does not. There is some overlap of the material, but very little, and much has been done, and I will explain what those other topics are. Okay, so those will be the abbreviations: MPA for Kay's book, and SOMOPA, the structure of models of Peano arithmetic. Look, but now what I want to say is that it's not, it's a beautiful subject. It's a subject that I like, but it's difficult to popularize. And it's difficult to talk about it even to logicians, even to model theorists who are not doing research in models of Peano arithmetic, because there is kind of a steep learning curve at the very beginning. One has to go through all kinds of preliminary materials, and Kay's book explains this very well. And then once you get over it, everything becomes much more pleasant and much more interesting. The preliminary material is tedious. There is lots of notation, lots of small details that have to be worked through. So there is I do recommend, there is Laurie Kirby, who also made extremely important contributions to the subject. In 1992, he wrote a review of Kay's book, and I just want to slowly read what he wrote. He wrote many interesting things about the book, and he praised the book highly. But then what he says I have to do something here because the Zoom is not letting me see the whole slides. Let me see if I can do something about that. No, well, I would like to minimize. Okay, sorry about that. Okay, Laurie Kirby writes that the model theory proper begins with the fundamental overspill lemma, the order type of a non-standard model, cofinal extensions, Geifman theorem, prime models, and extension, the McDowell-Specker theorem, and I will talk about all of that. And then comes the chapter that, as Kay says, no one wanted to have to write. And then he continues, the details of the arithmetization of syntax and semantics. The trouble is that probably no one will want to have to read it either. And I know how many of you tried. I know that some did. And he says, although Kay has wisely delayed it until unavoidable, I think he could have made it easier on the sedulous, diligent reader by presenting just enough to give the spirit of the enterprise and then relying on some intuitive comments to motivate the rest with details left as exercises and appendices. And look, so this is just a quotation, and I encourage everyone to reach out and read the whole. It's a very kind of lucid presentation of the subject, but it's just not difficult. So what I'm going to do, I have this quotation here because what I'm going to do is exactly what Kirby recommends here. So some technical details will have to be skipped necessarily, and I will rely on some comments, intuitive comments to motivate the material. And I also want to leave some material as exercises because this is the talk is for students. And so there'll be some propositions, some simple facts. And whenever I say that something is a proposition, it's actually, I would recommend for anyone who's interested to try to come up with a proof himself or herself, because these are just small exercises in the subject. Okay. Now, something about notation quickly. So we'll be talking about natural numbers. The standard model of arithmetic, I will use omega for the set of natural numbers and this blackboard n for the whole structure. And the structure means the domain, the set of natural numbers, and two functions, addition and multiplication. So the language, the first order language for this structure is just formal first order language with two function symbols for addition and multiplication. Now, not to make the notation too kind of extended, when I say that M is a model of PA, M stands for both the model itself, so this is the whole structure with those two functions on it, addition on M and multiplication on N, as well as the domain. Just to simplify the notation a little bit, this is the standard custom, not in textbooks, but quite often in research papers this is done. And then there is a little bit of confusion because if a model M is a model of PA, I write M with plus and M with times, not as expansions, but as reducts. So it means I keep the domain, but I forget about the other functions. So these are the additive reduct and the multiplicative reduct of a model of arithmetic. Okay, and no, just to say it formally, a model is non-standard if it's not isomorphic to the standard model. And we will talk much about definable sets. And definable sets can be in any dimension, and they are definable in the sense of first order logic within this language of Peano arithmetic. And definability, this collection of definable sets that includes all parametrically definable sets. So definitions may include parameters from the structure. Okay, part one. So look, so this has to start with Thoralf's column, although it's not from 1950s. This is in 1934, Thoralf Skolem wrote this paper in Fundamenta Mathematica in 1934. It is in German, and the article is not very well known. But what I have here is a quotation. The article is translated and published it was published in 1971. And here is the reference to it. And in that paper, Skolem wrote, that it was then to be expected that if we try to characterize the number series by axioms, for example, Peano's, using the reasoning with sets given axiomatically or what amounts to the same given in some formal system, we would not obtain a complete characterization. So here he talks about what we refer these days to categoricity, whether there can be a set of first-order axioms that characterizes natural numbers with the operations on them categorically, which means a system that has only one model. And Skolem wondered about it, and he says that by closer study, I succeeded, and it was in 1934, in showing that it is really so. This fact can be expressed by saying that besides the usual number series, other models exist of the number theory given by Peano axioms or any similar axiom system. And for Professor Chang's students, I know that you are looking, you're reading my book. My book is really sort of first introduction to model theory for beginners, as the title suggests, but I included the chapters that are usually not included in introductory sections, just to give some introduction to model theory of arithmetic. And the Skolem's construction is fully explained there in details in section 12.2. So you can take a look at it and see what Skolem construction was, more or less exactly the way he designed it. But Skolem was not interested in sort of studying non-standard models. He was just interested in this phenomenon that first-order logic is not really strong enough to characterize such fundamental mathematical structures as the natural numbers. Once you have a structure with an infinite domain satisfying certain conditions, then for any axiomatic theory there will be a structure that's similar to it, which means satisfying the same set of axioms, but not isomorphic to the even one. So this will be forever a fundamental phenomenon in mathematics now, that the intended structure will have some other for every intended structure, as long as it's infinite, there will be other structures that are similar but not isomorphic to it. Okay, and now, so then I will go over some number of papers from 1950s and 60s, and this one is by a Polish mathematician, Czesław Ryl-Narzeski. Something. Can you see my? Let's see. Something happens here. I have to. Sorry about that. This is the Zoom windows pop up and block the view for me. I don't know if they block the view for you. Hopefully not. Okay, so Czesław Ryl-Narzeski was a very prolific Polish mathematician, and you can see that he has lived a long life. And I actually met him. He worked in Wrocław in Poland. And I was there at a seminar, I think in 2011, when I gave a talk, and he was there. I was very happy to see him. He wouldn't describe himself as a logician or a model theorist. He was an analyst, and he has tons and tons of papers in various areas of mathematics. But early on, this is the paper from 1952 already, that he proved this fundamental result. The result is that Peano, we know that Peano arithmetic is an infinite set of axioms, and he proved the result that says that you cannot reduce this infinite set of axioms to a finite one. And the proof is model theoretic. It uses models of non-standard models of arithmetic. And here I have a quotation from a review of Ryl-Narzeski's paper by Abraham Robinson from Mathematical Reviews. And I have it as an example of how the language in which we talk about model theory has changed, because this is early 1950s. So the papers are not easy to read. Notation is different, symbols are different, and this is what Ryl-Narzeski says in the paper. Oh no, sorry, not Ryl-Narzeski, Abraham Robinson in the review. Okay, is that he says that following Skolem, we may interpret the notion of a property which occurs in the principle of mathematical induction for the positive integers as a predicate of one variable, which can be expressed in the lower functional calculus in terms of primitive relations and functions, some or all of the notions of equality, order, sum product, and so on. So this is a sentence that describes essentially what Peano axioms are. The induction principle says that this is the fundamental nature of the natural numbers, that if there are natural numbers having a certain property, then there is always a least number that has that property. And from this, the induction principle follows. So if 0 has a property, and for every number n, if n has the property, then n plus 1 has the property, then all numbers have the property. And it was the early understanding of the sort of description of what natural numbers are, except that it's not clearly stated what a property is supposed to be. And so now this is, in this one sentence, these things are narrowed now to what essentially is first order logic. So by property, we're just saying, well, anything that can be expressed in the first order language of Peano arithmetic. Okay, so then Robinson continues that writing down the principle of induction successfully for all these predicates, we obtain a sequence of axioms. If we add the usual rules of arithmetic and order, this is what we know now as PA minus. There results an infinite set of axioms for the system of positive integers. And the present author establishes the important result that an equivalent finite set of axioms for the positive integers does not exist in the lower functional calculus, even if new functors are added as primitive notions. And I underline this, an important part of the proof is played by what Robinson calls non-normal models of axiomatic systems for positive integers whose existence was first established by Skolem. And what I find it interesting here that Robinson himself, who's the creator of non-standard analysis and uses of non-standard models in mathematics in general, initially calls these non-standard models, what we call now non-standard models, non-normal. And and the paper is long and difficult. I read parts of it, but I didn't go through all of it. It's in a vast level of generality. But if you want to see quickly what the Nirzewski result is and how it's proved, using a short presentation is in Richard Kay's book. It's the theorem 10.2 in Kay's models of Peano arithmetic. Look, do you have any questions so far or comments? No. Okay, let's move on. Okay, so now I want to mention Andrzej Bostowski, who was a very influential Polish logician. He contributed much to many areas of foundations of mathematics. And already in 1953, he gave an address to the Congress of Polish Mathematicians. And then an extended version of this lecture was published in 1955. And this is really about the status of foundations of mathematics in 1950s. And among other things, he discusses this phenomenon of existence of non-standard models. And here's a sort of a program of what one would expect to get from non-standard models. So this is a quotation from the paper. So the purpose of research on those non-standard models will be, one, what kind of structure have the models of Peano arithmetic differing from a model composed of natural numbers? In particular, what is their ordinal number? And this order type like. Two, to find out whether using non-standard models, it would be possible to obtain proofs of classical number theoretic problems of the system of arithmetic axioms. And three, to prove incompleteness of axiomatic arithmetic without applying to the method of arithmetization by giving suitable models showing the consistency and independence of an appropriately chosen number theoretic axioms. Look, so this is really kind of prescient, that sort of, because this is more or less what happened. So on one hand, well, the research goes in essentially two ways. One is just to see what those models are good for, and whether there are facts that we can discover about the standard model by looking at properties of non-standard models. One of the major thing in formal arithmetic is the incompleteness phenomena. And then is to see whether non-standard models can be used to get insight into incompleteness in formal arithmetic. And everything that Mostowski here is writing suggesting to do, well, has to large extent has been done, in particular part 3 in 1970s by Paris, Harrington, Kirby, and others with combinatorial independent statements from Peano arithmetic, where model theory of non-standard models that plays a very important role. Okay, and now one of the
I have a question.
Yes.
On the previous slide. First of all, comment. It's amazing how already 1953, so many things that you and other people have developed, in Kay's book and the Schmerls is there. But number 2, to find out whether using non-standard models it'd be possible to obtain proofs of classical number theoretic problems. That seems to be. Is it correct to say that that's the least developed of these 3, or the most
Well,
problematic of these 3?
No. Yeah, no, this is, thank you, Andres. So this is a good comment. You need this, so the applications are actually there, but they're not that well known. There is the whole school, Mauro Di Naso gave talks to us about it. There are various Ramsey-like theorems, well, that are known to be true, and that have much more simplified proofs using non-standard models. Even recently, I think this is Renning Jin, and you can look it up because it's somewhat of a fantastic result. There is Semeredi's something density theorem. I don't now remember what the theorem
Yes.
says, but this is a vast, difficult theorem that has been, the proof was much simplified by using non-standard models with 3 levels of non-standardness. And I just went to a talk recently about it. I don't remember, but for simpler, like for example, proof of Ramsey theorems, infinite Ramsey theorem, can be given using non-standard models. And it's not that we're learning something new, but the results are, but the proofs are simpler. They are streamlined, and Terence Tao has been advocating this quite often. And Renning Jin, I mentioned, he specializes in additive number theory, where he actually did prove facts, the additive statements about addition of natural numbers, number theoretic theorems about infinite sets of positive Banach density and things like that. He can prove theorems about them that are new, that number theorists learn about them for the first time and they consider them interesting. So this has been done, but it is not that very well known.
Okay, so in that sense, so classical number theoretic problems more in the style of either combinatorial, Ramsey
Right,
style,
combinatorial, that's quite, this is well known and done, but this in additive number theory, they are not that well known because even statements are kind of complex. They are for specialists, but it works.
Yes.
Right, but anyway, so the thing is this, that so there's the utilitarian thing that you want to see what those non-standard models are good for. And the other thing that I will concentrate on is that we study them for their own sake. And I will try to explain why. Okay, so this is something that I titled my talk that, small steps and milestones, and there will be many. So real Narzeski can be, now these days can be considered a small step because it's, this non-finite axiomatizability of parallel arithmetic. It's a small step because the proof is relatively simple. But now Tenenbaum theorem is, a milestone really that. And this is from 1959. Tenenbaum never wrote a paper about it, but this is something that he announced in the Notices of American Mathematical Society in 1959. Just that, well, in short, you can say no non-standard model of Peano arithmetic is computable. But what it means is that you look at countable models, and countable model, it's the domain can always be the set of natural numbers. And now look, and here is this so a typo here. This thing here was supposed to be addition on M. I don't know what this comma is doing here. So we have natural numbers with some other addition and some other multiplication that makes it a model of Peano arithmetic. Every countable model can be represented this way. And then you ask, what is the addition and multiplication? What are they? What is their description? How do you know what A plus B is in a non-standard model? And Tannenbaum proves that neither addition nor the multiplication can be computable. So what's the importance of this? Well, the importance of this, first of all, I found out that this result had a history that's also interesting, and Mostowski is involved because Tannenbaum proved it in 1959, and everyone knows this is a fundamental theorem of Peano arithmetic. But Mostowski wrote a paper 2 years earlier in 1959, and this is a quotation from Georg Kreisel review of Mostowski's paper. The title is on recursive models of formalized arithmetic. And Kreisel writes, the proof of the main theorem in Mostowski's paper shows that there is no recursive non-standard model in which all theorems of quantify a free primitive recursive arithmetic are valid. So what it means is that Mostowski proves that if you make the language rich enough, so if you introduce enough functions and relations, but they're all computable, primitive recursive functions and relations, if you add infinitely many of them, or the full primitive recursive arithmetic, then the theory in this infinite language cannot have a non-standard computable model. But then Kreisel continues, why is this important? He says, in other words, recursive models are useless for independence problems in full primitive recursive arithmetic. Okay, this answers a question raised by Skolem at Amsterdam in 1954. It is not known if elementary arithmetic with addition and multiplication as the sole non-logical constants has a recursive non-standard model. So this last part, it's exactly the question that Tannenbaum answers. It's about the nature of addition and multiplication only, without introducing all those other computable operations. But it's interesting that the phenomenon itself is general. And why do these results make non-standard models useless? And it is because once you find out that you cannot have computable relations like non-standard addition, non-standard multiplication, what it means that you cannot construct these models in algebra using standard routine algebraic means. What you do with standard routine algebraic means you start with a computable structure like the natural numbers or the ring of integers or the field of rational numbers, and then you construct something upon those structures like extensions, but those algebraic operations take you from a computable structure to another computable structure. So, and you want to construct those models to show independence of certain statements, but if you only have computable means, you will never get something that will give you those answers. This was the Kreisel's view then, and this is the general view. So so this is Tannenbaum now. Okay, and now this is related to some other development, which seems like something completely different, something of more set theoretic nature. This is a paper of Dana Scott from 1962, and this is of algebras of sets by numerable incomplete extensions of arithmetic. So the paper was about, you have various completions of Peano arithmetic, and his question was, there's a notion of representability of sets in formal theories, and his question was what kind of what families of sets of natural numbers can be represented in various completions of PA or some other theories. But this leads to a concept of a Scott set. He didn't call it Scott set, there was some other name for it, but you look at a Boolean algebra of sets of natural numbers. So Boolean algebra, which means a set that's closed under unions, intersections, and complements. And such a Boolean algebra is a Scott set. First of all, it's closed under computability. If for every set in the algebra, if B is computable from A, then B is also in X. In the sense, in terms of formal theories, computability is the same as being delta one definable. There's another equivalent definition. If B is a delta one definable from A, then B is also in X. And then the second important condition is that it's about Koenig's lemma. And in this case is the question of weak Koenig's lemma. That suppose now the coding is involved. You're looking at the sets of natural numbers, but they can code arbitrary finite sequences of zeros and ones, and finite sequences of 0 and 1s form a tree. This is 2 less the omega. Less than omega is the set of all finite sequences of zeros and ones. And so it's a tree with a natural ordering on sequences. And the weak Koenig's lemma says that whenever you have an infinite tree like that, then it must have an infinite branch. And it's the weak Koenig lemma because you talk only about tree that branches, that two branches tree, finitely branching tree. And a set is a Scott set. If you have a tree whose set of codes is in X, then we know that this tree has some infinite branch, but the requirement is that it must have an infinite branch that's also in X. So the Scott set must be closed under infinite, taking infinite branches or infinite binary trees. Okay, so in these days, for those of you who are familiar with systems of second order arithmetic used in reverse mathematics, so this is equivalent to saying that a Scott set is a Boolean algebra. That's a model of what's called weak Koenig's lemma, WK is 0. Okay, and the key fact here, though there are many key facts about Scott sets, but one, and it goes back essentially to Gödel already, and actually more than Turing, Church and Turing, that there are infinite binary trees that are computable, but they have no infinite branches. They have no infinite paths. And so the corollary of it, I will show you what's the relevance of it, is that every Scott set contains a non-computable set. So for example, computable sets do not form a Scott set. Every Scott set must contain some non-computable set. Okay, and what's the connection? And so the connection is through another paper. This is a later paper by Harvey Friedman, and the title is Countable Models of Set Theories. So he talks, it's not, set theories is very broad sense here that includes the systems of second order arithmetic, some weak axiom systems for set theory. And Friedman was interested in non-standard models, but in particular, he defines a standard system of a model. And in the case of arithmetic, the standard system can be defined simply, you have some non-standard model of arithmetic, the standard numbers sit there as an initial segment. You look at all definable with parameters sets in this model, and you look at the traces, their intersection with the standard model, and this forms the standard system. In Richard, the standard system is a very robust notion. It can be defined in many different ways. Richard Kay uses something similar to what I have here. These are essentially sets. This talks about sets that are standard parts of definable set, but this definability can be of very simple nature. So here we talk about elements of a model that code sequences. And so AN is the nth term of a sequence coded by A. And you look at those sets, that can be represented this way. For example, if you look at 0-1 sequences, it's like a characteristic function. So essentially, this is a characteristic function. A codes a characteristic function of some infinite set, and you look at the intersection of this set with the standard cut, and then that set is becomes part of the standard system. So the connection is that standard systems are Scott sets, and this is an opening to this whole discussion of the Tenenbaum's phenomenon in general. Non-standard models of arithmetic do not have computable presentations, but what about other theorems, other theories, weaker theories, theories in some other language not related to arithmetic, and those considerations about standard systems. Actually, there is a proof of Tenenbaum theorem, and I will say more about it if there is time at the end. The connection to recursive saturation and other notions in arithmetic. But there is a discussion about how this whole investigation of standard systems and Scott sets leads to Tenenbaum's phenomena. And this is in Richard Kay's book on page 267. The title of this section is The Limits of Tenenbaum Theorem. Okay, but now, so now there's a little bit, we need to develop a little bit of machinery to talk about models in general. So this is something that's extremely useful. So Peano arithmetic has what's called definable column functions. So, here is a formal definition. You look at any binary formula in the language of arithmetic, and then to every formula that you associate a function. We call them column terms. So you think of y's as parameters. So this formula with some parameter y defines a set. And if this set is non-empty, then the function takes you to the least element of that set. It could be empty, but then by convention, this minimum is zero. So these column terms are interpreted in every model of Peano arithmetic as total functions. So now we have this term. By term, I will denote this collection of all column terms. And that leads us to a definition of a column closure. If I have a model of arithmetic and any subset of it, then it's column closure. You just take values of column terms on all the elements. I forgot to put no. Okay, here is a typo. So it's the value of all column terms where T is any term and A is an element of A. So you close A under those column terms. And this is this is reminiscent of Skolem-Levenheim theorem when you produce elementary substructures of infinite structures by taking closures under some kind of Skolem terms, either definable, not necessarily definable. But in case of arithmetic, these Skolem terms are so nicely behaved that if you just do it once, you don't have to iterate closing A under Skolem functions. If you just do it once, as defined here, then you form an elementary submodel of a model M. Okay, and so in particular, there is this category of simple or finitely generated models if simple if it's a Skolem closure of a single element. So those are simple models. Okay, so now comes Andrzej Ehrenfeucht. Andrzej Ehrenfeucht was a student of Andrzej Mostowski. One of the things about those Andrzejs, this is probably most misspelled name in history of mathematics. For some reason, the way you read this is Andrzej, but when you look in the literature, there's all kind of misspellings of this RZ. The sound in Polish is Z, Andrzej Ehrenfeucht. And I have the paper that the full paper that Ehrenfeucht wrote in 1973. This is the whole paper. I don't want to go over the paper, but I encourage you to do that because it's extremely well written. It's not like this is a complicated result and somehow reduced to some slick proof. The complete proof of an important result about simple models is on this page and a half here. And this could be it's really like the proof from the book. So I'll tell you what the result is, but I encourage you to look at the paper and its proof. What's the key here is what's known in the literature for models of arithmetic as Ehrenfeucht lemma. So here is this main result of Ehrenfeucht that put simply this way, that for any element if you take this column closure of a single element, and if it's not A, then the types, these are the model theoretic type, the type of B must be different from the type of A. Okay, so some simple statement, but it's important in this whole study of structure of non-standard models. So there are corollaries of it. So in particular, it shows that simple models are rigid. They do not have non-trivial automorphisms. Well, because automorphisms carry elements of a given type to elements of the same type, but type A cannot go anywhere because it has a type different from any other element. And if A generates the whole model, if A doesn't move, then nothing else moves because column terms are definable. So once every automorphism has to fix A, and if it fixes A, it fixes the whole model. And this generalizes to these elementary extensions when you start with a model and you take an extension that's generated by elements of the ground model and one new element. And so this structure and then becomes rigid over M, which means that if you have any automorphism of the model, if it fixes the whole ground model M, that it has to fix, it has to be identity, it has to fix N as well. So this is an interesting technical result. So on one hand, this is what I would call a small step. On the other hand, there is something quite fundamental about this Ehrenfeucht, sometimes called Ehrenfeucht lemma. Here I called it a theorem. And it's quite unique to Peano arithmetic, and it's very useful. It affects many properties that non-standard models have. Lisa, I have to pay attention to time. So I have to stop for a moment. Stop for a moment. Maybe you can think of some questions, and I have to leave and bring my phone with me so I can see what time it is. Okay, so think of some questions. I'm coming back in a minute. Okay, I'm back. Okay, we're doing. No, 2 hours is an awfully long time. When you get tired, ask questions, and we can take a short break. Let me know. Okay, look. So the next character here is Abraham Robinson, who, as I told you in the introduction, he was the sort of an influential mathematician. He was the sort of inventor of the non-standard analysis using model theoretic techniques, and then the various developments in model theory of arithmetic are due to him and his school at Yale on the East Coast in the US. And and this is like a separate subject, separate topic. This is a paper that Robinson wrote in 1963, and this is at the time when he wrote his famous book on non-standard analysis. He was thinking about non-standard methods in mathematics using non-Archimedean real closed fields as a base for doing mathematical analysis and transfer principles between standard models and non-standard models. So and it's a beautiful paper. It's a long paper, many pages, but there is not that much material in it because Robinson explains everything in excruciating detail, because it's a new idea, and he has some thoughts about how to use it, how to develop some sort of non-standard model theory. But it takes time to develop even a proper vocabulary, what it possibly could mean and how to think about it. So here is a very brief outline of what he had in mind. That we have these formulas of the language of Peano arithmetic. You have terms, and then you have arithmetization. You have Gödel coding of the syntax of Peano arithmetic. So you can take these formulas that represent in Peano arithmetic, this is a formal statement, represent means that every Gödel number satisfies the formula, and no other elements, no other natural numbers do. You have representation of these objects, the codes of these objects, formally in Peano arithmetic. So now if you have a model of Peano arithmetic, you take these formulas and you see what kind of objects in a non-standard model satisfy these formulas. So that would be all the standard formulas and all standard terms, but there will be also non-standard. And how do we know that? Because Peano certainly is strong enough to know that these sets are unbounded in the standard model. So if these sets are unbounded in the standard model, they have to be unbounded in every non-standard models, because they are models of PA. So in a non-standard models, there will be lots and lots of objects about which M thinks they are Gödel numbers of formulas. You can think of them as formulas. You can think of them as terms and other, sentences or proofs and all kinds of syntactic objects. So in my book with Jim Schmerl, we have this convention. No one really defines, says where the formulas come from in the set theoretic setup. Well, everything's a set. So formulas, sentences, terms, they are some kind of sets in set theory. In arithmetic, we have this way of coding formulas and sets and sentences and terms as numbers. So we might as well think of those terms and Gödel codes as formulas and terms to begin with. So it's a useful convention, because then you avoid this notation, with this upper bracketing to differentiate between actual formulas and their Gödel numbers. But anyway, so the idea is this, that in a non-standard model, you have all these non-standard formulas and terms and other syntactic objects. And the very general and vague question is there a semantics? So is there some way, so for example, if you think about sentences, is there some way to sort of divide all sentences of a non-standard model into true and false in some sense? And the sense would be that you divide them into those two classes, and you want the negation of every true statement to be false, and the negation of every false statement to be true. And you also want them to satisfy all the usual clauses of Tarski's definition of truth. And it turns out that this was a very fruitful question. And the answer is not always, but I will not be able to explain that fully. So I will just say that. But what Robinson includes in the paper, and he's very happy about it, is Robinson's proof of Tarski's undefinability of truth theorem. And so here is the outline of the proof. And I will go over it because this is an example of, what Robinson might have thought about when he was thinking about those possible interpretations of non-standard languages in non-standard modes of arithmetic. So, so this is the simple version. The Tarski theorem has many versions of generality. And recently, Ali Enayat, at CUNY here, we have now this online seminar known as MOPA. I will give you a reference later. And recently, the recent two talks were by Ali Anayat, who there are some interesting developments about Tarski's undefinability theorem, its status, and various proofs of it. So it's a beautiful talk. So I encourage you to take a look. We have everything recorded, and we have a YouTube page for our seminar. But here's one of those ways of looking at Tarski's theorem. You look at the standard model, and you look at the set of pairs of numbers. Okay, this is the Gödel number of a formula. This is a natural number, and you take the set of all of them. This is essentially the standard satisfaction relation on the standard model. Okay, so what kind of set is this? And whatever it is, Tarski's theorem says that this set is not definable. There is no arithmetic formula that would define this set. So here's the proof. Okay, suppose that there is a formula that defines exactly this set. Okay, so the formula that if m and n satisfy the formula in the standard model, that m is a Gödel number of some formula with one free variable, and this formula, say some formula phi, is true at n and satisfies that formula. So, okay, but the proof is model theoretic. To prove the theorem, we take an elementary extension of n. So how do we make those elementary extensions? I will talk about it in detail a little bit later, but this is simple compactness theorem. You just take any elementary extension, and they exist. This is like Skolem. You take the Skolem's construction that gives you an elementary extension, but you want it to be simple, which means you want it to be generated from a single element. And if it's not, if this column construction doesn't give you a simple model, which it actually does, but if it didn't, then you take any non-standard element and you close it under column terms, and then you get a non-standard elementary extension of the standard model that's simple. So this A is a non-standard element. So now what is true in this model, look, this statement here, the theta defines satisfaction. for every parameter y. So now for every single formula, this is a single sentence that's true in the standard model. It just says that theta defines satisfaction for each formula phi separately. So this sentence is true in the standard model, and because this model M is elementary extension of the standard model, this is also true for the non-standard elements as well. Okay, so now, and but phi here is a finite standard object, a formula. But now you look at it this way. I take some liberty here with notation. It has usually those formulas look more complicated. As Laurie Kirby said in his review, there are some technical details that one has to worry about, but we will not worry about them. We'll just look at this sentence here. The sentence says that there is an element z such that for every t, now t is a term, but if we also say that t is less than chosen in advance standard numbers, then those t's are standard terms. So we're talking about finitely many standard terms. And now we're saying, oh, for finitely many standard terms, there will be some element z that's different from the values of this t on A. So it's just you want to have this z to be different from t of A for some finite set of terms t. And this is expressed, and theta knows about it. This is the formula. So I write this formula instead of its Gödel's number, because then it would become notationally complicated. But it says that there are two free variables, y and x. Y is this parameter A, and z is this z that we have here that exists. So there is z that's different from all the finitely many t of a's. So it's a clearly true sentence, but now with this parameter n, but now there's this overspill principle. If in a non-standard model there's something is true for all standard numbers, then it must be true for some non-standard element. Okay, so you overspill. Now it becomes a little bit of a mystery what the meaning of theta, this interpretation of this formula theta, how it operates when t is less than c but non-standard. But we don't care, because something here is true for all t less than c. So in particular, it is true for all standard t. But then what is this formula saying? Well, it's saying that the value of all the terms on A for all standard terms is different from the z that exists. So it means that there must be some z that's different from all those standard TAs. But that's contradiction, because M is made of all those standard terms. Okay, look, so any questions about the proof?
Hi, Roman, there's a question from the chat box.
A question where?
There's a question in the chat board from Vincent and Blazy. He asked, is the set defined here with unary phi just for this proof?
Is the set defined here using phis instead of nullary is for this proof? No, this is there are many variants of this proof. You mean why is it binary? It's just to avoid coding. I could have, typically this would be like a single number that, it's a complicated situation. Now there is the whole, as you know well, that now there is this whole study of axiomatic theories of truth, and it splits into axiomatic theories of truth when you talk about sentences with numerals. Then you represent all elements of your model. So typically this n could be sitting inside here as a numeral, because it's a sentence, it's a formal object. So we'll be talking about unary set. Okay, but then again, it requires again another level of formalization, of substitution of numerals into formulas and things like that. So here is the simplest formulation that I talk about satisfaction. And in satisfaction, you talk about pairs. And it doesn't even need to be a coded pair. You talk about pairs, a formula and a parameter. And so this is your satisfaction relation. N satisfies phi of x. Okay, this is this relation that is coded by this set. And this is the very simple formulation of Tarski's theorem for this setup. But it's very easy to adjust the same proof for all those others. This could be about truth, it could be about satisfaction. These are just some small technicalities. that make notations a little more complicated. So this is here I'm avoiding notational complications. But if you want to have the unary, if you want to.
Okay.
Oh, why coded
One question.
coded? Yeah, right. But that's what I mean. I could be using sentences, but then it's just a level of notation that goes up. Okay, but one thing about
question.
yeah.
Oh no. Yeah, where do you use exactly that M is a simple elementary extension? I think you use A here, and I'm just marking
Here.
it.
Right. So right. Because these formulas are saying X is different from any finite set of T of A's. And this sentence says that this Z is different from all the T of
Oh,
A's
okay.
C,
Because
in particular,
why?
all
I mean,
standard T's.
why is the whole second thing here? This would be Y somehow.
Right. So A is
Okay.
Y and Z is
Oh,
X.
A.
Again,
Okay.
because we have formulas. So this really should be a Gödel number. So the formula for standard formulas, it could be, this is really, again, but I didn't want to put those extra layers. So I said, this is really
Yeah.
abuse notation. Here is a
Okay.
Gödel number of certain formula. It includes non-standard formulas here of this shape. The set of non-standard formulas of this shape is definable. We know what it means.
Because uh, I'm just trying to think of this as a template for other variants of proof of undefinability of
Yes,
proofs
yeah,
in different
exactly.
structures.
No,
But the structures here have a very specific form of
right,
that you have simple elementary extensions.
right,
You might have many situations where there are no simple elementary extensions.
right.
Therefore, you not.
Right.
But
But look, but there is more here. So since because it's interesting. So first of all, Robinson, he just gives this as an example of how non-standard formulas, because for non-standard T's, this is a non-standard formula. How this non-standard language can be useful to prove something about the standard model. Because the theorem is about the standard model. It's not about, this is some kind of fictional M that we use here, but the conclusion is about the standard model. But there is much about this proof. So first of all, Robinson is happy because you do not see this direct appeal to any diagonalization here. You don't use the diagonal lemma. You don't use, the liar's paradox. It's just you use a non-standard model to prove that something cannot happen. So
but
that's one thing.
overspill is a way of coding
Overspill is a standard.
liar.
Overspill is standard tool. It's a direct consequence of the induction principle.
But
So
overspill, in a way, is kind of playing the role of what would be played, by the liar's paradox. Somehow, here it allows you. I mean, the C here is kind of a meta diagonal, so to speak. Kind of,
no,
it's
but
playing the role.
the C just no, it's not diagonal because you're not diagonalizing. You're just extending this into infinite. You have the
Yeah,
sequence, so you're not changing anything. You're not coding some kind of a fancy diagonal argument by some
yeah.
C. You're just
But
extending this to infinity. So this is like an
but
ideal element for. This is the essence of compactness here, really. It's not
yeah,
diagonal. It's
because
compactness.
the proof here is it's very similar to like the Erdos-Rao proof, the ball theoretic proof of Erdos-Rao or all combinatorial statements, where you take the average type. But the average type, in a way, when I say it is kind of replacing diagonalization, it is because in a way it is
Right, because
capturing an
because
essential
but
feature of all
yeah,
these
right.
ends.
So you're taking something generic or something. No, but here
Yeah,
this is much more simple-minded. You just extend something to infinity. That's all. You want to be able to talk in a the thing is that this is not a single sentence because this is a one sentence because you're talking about M. So
yeah.
there is just one sentence for each N. Or there is a formula, and this is sort of you evaluate at different standards N. So you cannot combine this information here into a single sentence because you would have to have this infinite conjunction. But because you can overspill, you say, oh, this must be true for some non-standard C as well. And so now the meaning of this is cryptic because you don't know what is really theta saying about non-standard T's. But we do know that what the sentence is saying about standard t's, because all the standard t's are included here, is this. For standard t's, this means what it means. The meaning of this and this for standard t's is just exactly the same. So because that's what theta is, because it represents standard satisfaction. So it allows you to say something about the standard satisfaction in M, which is a contradictory information.
Yeah.
But look, there is much hidden in this argument, because instead of overspilling something like this, so this is used to show that, first of all, this theta does not have to be definable, because here we use the fact that it's definable, but it has this property that it represents standard satisfaction and is definable. But if we forget about definability, but we require this condition and induction that would hold, it is also true. So it means that simple models cannot have inductive sets. It cannot have a set of pairs for which induction is satisfied that has this property. That's one thing. And the other thing is that instead of this, you can overspill some other properties. So for example, here you can have a type that's consistent and somehow represent that in the model, like a computable type. This is the origin of recursive saturation, quite long before recursive saturation was even born. Instead of this, you can have a condition, you have a type, and you say, oh, there's an element that realizes every finite fragment of the type here. And then you overspill, and then there must be an element that it realizes the whole type. So this is some notion of saturation is already hidden here. And these models are very far from being saturated. Finitely generated models are not saturated. So it shows that if you want to have some relation that satisfies certain assumptions, something like a non-standard satisfaction class or a non-standard truth predicate, then you cannot get it on all models of PA. M has to be somewhat saturated already. So that's, I'm saying this for those who know what I'm talking about. Frederick does, and you do too, Andres.
Well,
okay, so this is a very potent, it's a simple, potent argument. Okay, but I just wanted to mention it because we're talking about model theory from 1950 to 1975, and this is really a very early development. This theme has been, really, it's a sophisticated theme that much work has been done on those things. So let's see what else there is. Okay, now, but early on, the whole point was to we have some models, we have compactness theorem, we can generate some other models, but the general theme was, can we classify all those models somehow? Can we have some classification theory, divide them into classes and say every model is either like this or like this or like that? And a powerful tool in doing that is creating extensions. You have a model and you want to construct a new model based on it, a ground model and its extension. And what turned out is that, there are different kinds of extensions, and there is something hidden already in those definitions of what those extensions can be. So first of all, not necessarily elementary extension, but just an extension. And so extension is an end extension if all new elements are above all the old elements. So you only add elements on top of the model you started with. Well, it's a cofinal extension is the opposite. If you have any new element, there will be some old element above it. So in terms of ordering, if you take the supremum of elements in M, you will get N. So the M sits cofinally in N. So these are cofinal extensions. But then there could be mixed extensions, neither end extensions nor cofinal extensions. And an important notion turned out to be of a minimal extension. So you extend the model somehow, you go from M to N, and the extension is minimal if there is nothing in between. If you have any model that sits in between, that is either the small model or the large model. There is nothing in between. You just do one step in extensions. And simple observation is that all extensions of the standard model are end extension. You cannot add any new elements between 2 and 3. Okay, nothing can go between 2 and 3. All right, so this is just some terminology. And a result that I particularly like is that recently we had Mateusz Wewyk from Warsaw. He solved some problem of Dino Roseger and Stefan Lem, something in classification of isomorphism types of models of arithmetic, and they are descriptive set theory complexity. And he talked about this particular case for simple models, finitely generated models. And the talk was sort of, the assumption was that those simple models are somehow simple, the simplest models of PA. But it is not so at all. They are simple because they're generated by a single element. But here is this kind of notion that Jim and we defined based on some results that were already in literature. You look at an extension and we say it's super minimal if every element of the extension generates the whole model. But now, so this can only apply to countable models, because if n is uncountable, it cannot be generated by a single element. So this is a notion only about superminimality, is only about countable models. And the theorem, we have a proof of this in the book, but it was implicit in some earlier results by Julia Knight and Mark Nadel and Jeff Paris, but without isolating the notion and the dilemmas about it, that every countable model has a superminimal elementary and extension. So it means that and there are some very complicated models. There are recursively saturated models. There are highly non-finitely generated models. Your model, every means every, as complicated as they come. And you can always find an elementary extension that's not only simple, it's simple using any element of the extension. Every element of the extension knows everything about this model you start with. So this is the enormous power of arithmetic, that a single element can code the whole very complicated model. So that's sort of why I say simple models are not so simple. And it's interesting. There is in the proof. So this is in our book. You can look it up. But there's a key lemma which is interesting on its own. And this is for any model. The theorem is just for countable models, but in any model, you take an element in a model and take any unbounded definable set, any whatsoever. Then you can construct, and this is tricky. Jim Schmel came up with this nice construction. You can construct an unbounded definable subset of X such that there is a Skolem term T of Y, that T of B is A, and this should be Y. Sorry about that. I promised Young that I will send my slides. I will have to correct those typos. This is Y. Okay. So it means you have every unbounded set. There's some other unbounded set in it, definable, such that every element in it defines an element of the models chosen in advance. This is somewhat unexpected, somewhat unusual, and it works for every model of PA. So in particular, it has this interesting. I was asking these questions. That sort of, it's not that easy to answer this question without doing something like this. That if you take any unbounded definable set, then the Skolem closure of that set is the whole model. It's somewhat unexpected. No matter how sparse this set is, as long as it's unboundable, the Skolem closure of every definable set is M. Okay, so there are some technicalities. So this is what I would call small results. Those are not big steps. They are not milestones of model theory of arithmetic, but it's an interesting small result, and it has interesting consequences. Okay, but now it's a milestone. This is something that's considered a milestone, and it is a milestone. And again, things, much was happening in Warsaw, Poland. This is a theorem of McDowell and Specker. And you might have noticed that for people who are no longer with us, I have the dates. So you have some idea, who did and what. Nothing, unfortunately, we know nothing about McDowell, Robert McDowell. It's very difficult to find any information online. Jim Schmel was looking for McDowell. The paper is really not about models of arithmetic. The paper is on what's called Z groups. You take the group of integers, and a Z group is a group that's elementarily equivalent to the group of integers, additive group of the integers. And there's some questions about models of the theory of Z groups which models of the theory of the additive group of the integers. McDowell and Specker answered that question. And the story was that they met somewhere in Berkeley before 1959, worked on it, and wrote this paper. The paper is in German. And this was really a paper about Z groups. And this is something from the mathematical reviews, the review of the paper by Hilary Putnam. And he says the proof of this result, which is this result about Z groups, depends on an extension of a method due to Skolem. And this is what we talked about earlier, that in essence, the method is to form the ultra power. This is the ring of all first-order definable functions, modulo some appropriate ultra filter. But what Skolem did it over the standard model, N, okay, of the definable functions and an ultra filter of definable sets, everything done in the countable setting. The whole point here is every. And it's hard to see how to generalize Skolem construction into transfinite. You have to work over sets of large cardinalities. It's not quite clear how this can be done. But as Putnam says, this ultra filter with the required, finding ultra filters is difficult. You know that without the axiom of choice, okay, that there might be set theories that were ultra filters, even on the full ultra filters on the set of natural numbers. Non-principal ultra filters may not exist, but here they always exist. It's an uncountable ultra filter with the required properties is obtained by ingenious construction. So. In Richard Kay's book, all details of this construction are given, but I'll tell you a little bit more about it in a moment. And Putnam also says that little previous acquaintance with model theory is required. It's really a very direct construction using the strength of Peano arithmetic in a beautiful way. So it was, it's hard, this is what looked like the sort of really a milestone of various developments. And one corollary, for example, that, because it applies to every model. So you can start with any model you want. It has an elementary extension. It has an element, the extension has an elementary extension. You iterate it. You go to a limit step. You take the union of a chain of elementary extensions is elementary. The union of end extensions is end extension. So you can produce those extensions forever. So in particular, for any uncountable cardinal, every completion of PA has a model of cardinality kappa that's known as kappa-like. So the model is cardinality kappa, but every proper initial segment is of smaller cardinalities. So these are like thin models that can have any cardinality. I remember that when in my PhD thesis, which was long time ago in Warsaw, I had some results about omega-1-like models. And Paweł Zbierski, a Polish logician, was on the committee. And one of the questions, you are asked various questions, and then at the defense, he asked me about what's the point of studying uncountable models of arithmetic? And it's a good question, because arithmetic is supposed to be about natural numbers, and the set, countable set, and all kinds of things like that. And suddenly, we talk about these, large model and uncountable models with all kinds of set theoretic properties. I'm not quite sure. I don't quite remember what I answered, but I think the answer was essentially based on the fact that we asked various questions about these models, and the answer turned out to be interesting. And maybe I'll give you some examples later if there is time. But another answer that I could have given, that really with these kind of constructions, model theory of arithmetic becomes part of general model theory. Jim Schmerl proved some, the conjectures by Sikorsky about real closed fields with some additional properties, something that's used in non-standard analysis. Using non-standard models of arithmetic, you can construct other algebraic objects that are of interest to algebraists, and in particular, these sort of various kind of large models of arithmetic become integer parts of real closed fields, and that leads to interesting development. So here is an outline of the construction, but I just essentially said what it is. You just start from any model whatsoever, and you keep iterating producing those elementary and extensions forever, and you obtain interesting models. Okay, but now here's the next milestone. So, well, actually, two of them. There are two papers of Chaim Geifman. One is from 1972, and it's called as Geifman's splitting theorem. And it explains a little bit about what the whole theory of models of arithmetic looks like. If you take any elementary extension, then there is a unique model that's in between, that you can always start first by extending M cofinally without adding any elements above it, and then proceed by producing an end extension by only adding elements above K. So in a sense, it explains all kinds of things about the structure of these elementary extensions. And this is actually how the history went, that there is a theory, all kinds of theories of constructing cofinal extensions, followed by theories of constructing end extensions. And there are like different disciplines. And but in particular, I see. So that's one. And the proof of it, it could be an exercise. It's really, you just use proofs of just elementary model theory is enough to sort of, with some small things about Skolem terms, to prove the splitting theorem. But here is a hard theorem, that if you have two models and you assume already, now here, this is an elementary extensions. If one is a model of Peano, then the other is a model of Peano. But here, if we have two models, and you need to know they are already models of Peano arithmetic, and one is a cofinal substructure of the other, then it must be an elementary cofinal substructure. You cannot change the first order theory of a model by constructing its cofinal extension. All cofinal extensions are elementary. So no independent results, nothing interesting can be found by constructing cofinal extensions. You have to look at end extensions, not elementary extensions to look for any kind of independence phenomenon. And what's interesting about this theorem, this could only have been proved, Geifman's paper is from 1972, and it followed, this, historic event, Matiasevich, Robinson, Davis, and Putnam. They solved in the negative Hilbert's tense problem. The theorem is known as MRDP. Okay, something about undecidability of Diophantine equations over the integers, existence of solutions to Diophantine equations. This is a major development in even in number theory. But what's actually quite attractive here, and there are not many examples of it, this is an exercise in Kay's book, exercise 7.6, and if you want to look it up, that this theorem stated this way is in a sense equivalent. If you knew that this is true, that there is not a difficult proof that you could derive MRDP from this statement. So this is very attractive, but it shows that you couldn't possibly prove it without knowing the theorem. The theorem is extremely difficult and long, and it has all kinds of special things in it. So this is an equivalent version of something that's about solutions of equations to Diophantine equations, and a pure statement about model theory of arithmetic. Okay. Now, again, something here from that's related, still from 1970s. This is a paper that Jim Schmel wrote in 1973. Jim Schmel knew everything about these developments, McDowell-Specker. No, McDowell-Specker was a long time before that, but then Geifman. Because one of the things about Geifman's theorem, the one that's coming up. Okay, so this would be later, that Geifman was at Berkeley at the same time when Jim was there. So then there were seminars where those things were discussed. And one of the things about Julian Knight was also there, and other logicians who sort of grew up as disciples of Alfred Tarski and Vaught. So Jim wrote this paper, and it wasn't really noticed. It was ahead of its time. This is a version of McDowell-Specker theorem, but it adds something to it, that not only every model of PA has an elementary end extension, but the extension is conservative. And what it means that if you have a parametrically definable set in the extension, and if you take the intersection of it with the ground model, it's already definable there. And what Jim does, this is the outline of the proof. Actually, this is supposed to be the full proof. This is more or less what Jim states in his paper. And I will not go over the details, but there's some, you would have to sort of read this carefully and see what it says, that the statement here is actually a theorem of PA. What is said here, that for every formula, there is another formula with certain property, okay? Now, so one has to read it carefully, but the essence of it is that these formulas are used to construct a type, okay? And the type will be, you start with any model of PA, and how is this type? This is a unary type with parameters from the model, and it's a definable type, which means that for every formula, if you look at the set of parameters with which the formula goes into the type, this set is definable in M. So you define a type. The type is something external to the model. You describe a non-principal type. It will be a new element realizing the type. But for every formula, M knows with which parameters this formula goes into the type. So this is a formal definition of a definable type. This is something that Geifman did in a paper later, but already announced, and I must have talked about it earlier at seminars. It turned out to be a very, very powerful definition that's it also in general model theory, the idea of a definable type. But and if there are some students of Professor Chang who are still listening, I know that you are also reading parts of Richard Kay's book. And this simple proof already proves McDowell-Specker theorem. So you can see that just few clever lines, and it should be compared with full details of proof of McDowell-Specker theorem in Richard Kay's. There is nothing wrong with Richard Kay's proof. Richard just explains in detail what the original construction of McDowell and Specker was, but essentially what suffices to prove the theorem is what's on this slide here. Okay, look, so now what I see, this always happens with talks. It's 8:30 now. For me, it's also 8:30 for you. I should leave about 15 minutes for a discussion and questions. So I will skip some of the material that I prepared that gets a little bit more technical. And I will just give you an outline of what I was going to say beyond what I said already, and maybe concentrating on some highlights. Because this is something. So part 2 is supposed to be now really sort of going back. So all of it was sort of, it's already everything that I said before is in Richard Kay's book and some papers from, the 1970s and 60s. But now it's more this other direction in Mostowski's program, that we have those non-standard models, and how can we describe their structure? What is it that we talk about there? And there are many things we can talk about. So this already Mostowski mentions what is the order type of the model. That's an isomorphism invariant. Those isomorphism invariants, ideally, we would like to have some set of isomorphism invariants such that if you know some of those invariants, or maybe all of them, maybe you can pinpoint, maybe you can determine the model completely by a set of its isomorphism invariants. It turns out to be a completely futile task. Whatever invariants you come up with, you will be able to construct non-isomorphic models with exactly the same sets of those invariants that you chose. So in this sense, now it's well known that in model theory these days, like completely two different branches: the classifiable structures and non-classifiable structures. Sometimes the classifiable, sometimes you refer them to as tame, and I refer to those unclassifiable as wild. So models of Peano arithmetic are certainly on Peano arithmetic, certainly on the wild side, but on an incredibly wild side. Is the wildest there is. No matter how much you pinpoint the structure by doing those invariants, you can always produce non-isomorphic models with the same invariants. So so the order type, the standard system that we already talked about. Then you can take a look at the set of elementary of just cuts, initial segments ordered by inclusion. This is an ordered set. But you can also look at those that satisfy some specific theory, like PA or maybe some other theory. And all of this has been done. There's a whole, there's a series of papers where these things are carefully studied. Then there is this whole area that if you look at a given M, you can look not at cuts, but at elementary submodels in general. It turns out that these elementary submodels ordered by inclusion form a lattice in terms of lattice theory, and you can sort of study those lattices, and there is much to be said about it. And it turns out that much what's happening about those lattices is already follows from what you can say about finitely generated elementary submodels ordered by inclusion. And strangely enough, this is not a sublattice. It's just this upper semi-sublattice, but there is much that can be said about it. And then you can look at structures that some models are rigid, but some models are not, and some they admit automorphisms. And you can say, well, what can we say about automorphism groups of possible models of PA? So I will stop soon, and I will leave time for questions, but I just want to say something about the things that are well known. So, for example, this is like what Mostowski was asking, and I think he knew much about it already. That if you look at the order type of a model of PA, that it looks like on the picture here. This is the notation here, but what it means, you have your non-standard model. It has the standard part. And then you have an order set of copies of integers. And those copies of the integers, ordered sets here, there are densely many of them. Okay, so there is not the least one, there is not the last one, and in between any two, there are others. So this is a dense set. So, and this is an exercise. I called it a theorem, but this is something for those of you who are students. You can try to do it as an exercise. It's not a difficult exercise. That if a model is countable and non-standard, then this order type of the set of copies of Z is the same as the rationals with the ordering. It is also a sort of exercise that's it's a little harder, but not much harder, that if you look at, okay, so for the countable models, we know that there is nothing that differs between a model and another model. They're all copies of the rationals. It is not so for uncountable models. There are all kinds of things that can happen there. But unlike the rationals, you cannot have a model in which these copies of these are ordered. This ordering cannot be complete. What's underneath the in case for no M, the order of the D is the real numbers. And what intervenes here is some saturation property of the reals, the completeness. So what one can do also, this is an exercise. And it's interesting that, Harvey Friedman wrote in 1975 an interesting paper. And the title is 102 Problems in Mathematical Logic. You can look it up, 102. And on that list, the 14th problem is this, which is somewhat curious that he already thought about this then in 1975, that take completion of PA. And let this be the class, the class of order types of ordered redux of models of T. So you look at those, essentially you look at those orderings of D for all models of T. So look, so this is all about, all these models are models of Peano arithmetic. For countable models, we just have one order type. The question is that can the theory, the particular completion of PA, have some impact, can make a difference between the order types, between classes of, okay? So in other words, whether this spectrum of order types of models of T depends on T, or are they all the same? And much research has been done on this. The problem is still open. Richard Kay works on it. Andrei Bovikin, his student, wrote a PhD on this problem. And it's intriguing that the problem is still open. And so, okay. Now initial segments, there is much to talk about initial segments. I'm skipping that. And maybe I will finish because, we're getting close to the mark. I remember in my early days, when I was sort of involved in this sort of some research on models of power and arithmetic, and there was my colleague and friend Jan Krajicek from Prague, who was kind of skeptical about study of models of arithmetic, and he says, "Look, but Roman, but tell me now, what is the problem? The discipline is always driven by open problems. So what is the most important problem?" And I think this is generally assumed that the most important problem, open problem, still is the Scott set problem. There are reasons why the Scott sets are important, but so let me just remind you that what a Scott set is. So a Scott set is just a Boolean algebra of sets of natural numbers, and which is closed under computability, relative computability, and has this weak Koenig's lemma property that that you have a set of codes of an infinite binary tree, then that binary tree must have that's in the Scott set. Then this binary tree must have an infinite branch whose set of codes is also in X. And then we have this notion of standard system. These are just traces of definable sets in M on the standard path. So the Scott set problem is every Scott set the standard system of a non-standard model of power and arithmetic? So Scott proved that the answer is yes for Scott sets, and even for every countable Scott set, if you look at various completions of PA, this model can be a prime model of a given completion of PA. They can be it's a very small class of models that already is witnessing the yes answer, that you can realize those Scott sets in very small, in particular in simple models. Okay, and this this was used to lift the argument for a Scott set of cardinality Aleph1. This is by some kind of continuous elementary chain construction. That was done in a paper by Julia Knight and Mark Nadel, but independently it also follows from a lemma that Ehrenfeucht proved that the answer is yes if the Scott set has a cardinality Aleph1. So in general, so the problem is solved if continuum hypothesis holds, but if continuum hypothesis fails, there are lots and lots of Scott sets that have of cardinalities between Aleph1 and continuum, and the problem is still open. And set theorists are aware of this problem. It's really a problem of, and I remember I talked once to Stevo Todorcevic about the problem, and he quickly understood what the problem was, and his opinion was that the current methods using forcing methods in set theory are not really suitable to answer the question. Recently, there was some work by Elliot Glaser, who's still a PhD student at Harvard, that shed some light on the problem that it seems to have a sort of negative answer, but it's this is still work in progress. And Elliot Glaser, he gave a talk about related questions and our seminar not so long ago, and you can find it on MOPA. So I just want to finish. I have much more to say, and maybe at some point I can tell you the rest, but I just want to. Okay, so there is much more, and I'm not going to say anything about recursive saturation resplendent, but I want to say that at the end, okay, then, so I, together with my colleague Attar Abdul Kader, we're running this online seminar called MOPA. And we have a YouTube channel. You can Google it and find a NY Logic YouTube channel. And it's joined together with set theory seminar and some model seminar talks. So there are lots and lots of talks recorded there. But so if you look for MOPA talks, I gave a series of talks on the history of the subject, on various aspects of it. But 2 years ago, I asked Laurie Kirby and Ken McAloon, who both were important in the development of the subject, to give talks about the history of the subject, and those are very nicely prepared talk, and they are much different from what I talked about. There is much one can talk about, and you haven't seen yet what I was planning to talk about. But even with everything I have been planning to talk about, there is still much more. And there are two talks. So Ken McAloon gave this talk, A Pluribus Unum. This is about how in model theory of arithmetic, set theory, computability theory, model theory are combined. And there are various aspects of all those theories that somehow influence model theory of arithmetic. And there is also some reverse direction. And Laurie Kirby, who was, those first independence results, Harris and Kirby's papers on the Hydra and the Goodstein sequences. So he talks about this very specific topic that I didn't say a single word about. And the title of the talk is The Winding Road to Mathematical Independence Results for PA. And it's a very sort of informative and a very nice talk. And I recommend this to everyone. So I think I will, it's 8:45 here. I think I will stop here. Or maybe before stopping, I will tell you, I'm also scheduled to speak here next week. This will be about something that has to do with arithmetic, first order arithmetic, but the talk will be completely different. This is, I was preparing a survey, and it's such a vast area. I had to make choices, what to talk about, what not to talk about. And the next talk will be about something very simple, essentially a model theoretic analysis of the successor relation on the natural numbers, and the role of first order logic, and also the possibility of using some other extensions of first order logic to talk about undefinability results in arithmetic. So this will be next week. So I just want to tell you that this other talk will be completely different. It will be sort of, I will present some proofs that hopefully will be easy to follow, and there will be some results that you may find interesting. So I will stop here just to see if you have any questions.